Hi everyone, I'm delighted to present our work on physics-informed temporal alignment for auto-regressive PDE foundation models, addressing how to maintain physical consistency in neural PDE solvers while preventing error accumulation during long-term predictions. Foundation models have gained tremendous momentum across computer vision and natural language processing. In scientific computing, PDE foundation models offer compelling advantages. First, they enable few-shot generalization to novel scenarios through multi-physics pre-training, unlike traditional methods requiring complete redivision. Second, they rapidly infer high-accuracy solutions from coarse inputs, overcoming computational bottlenecks of finite element methods in high-dimensional systems. Third, they represent a step toward general scientific intelligence by mastering mapping operators rather than learning specific equation solutions. Now, you might wonder, how do we connect PDE data to the auto-regressive framework that has proven so successful in other domains? Solving time-dependent PDEs is fundamentally a temporal sequence generation process. Solutions at t+1 depend on previous solutions, like token-by-token generation in language models. However, PDE data differs significantly from typical sequential data like text or video. While text generation optimizes for diversity and creativity through cross-entropy minimization, PDE prediction requires precision and uniqueness. Given fixed initial conditions, boundary conditions, and governing equations, the numerical solution is deterministic. This distinction becomes problematic when we observe the error accumulation behavior. Auto-regressive approaches often suffer from severe error accumulation, particularly in systems with low structural similarity between adjacent time steps. The model tends to copy previous frames rather than learning the underlying physical dynamics. This brings us to a crucial realization. By incorporating physical priors inherent in PDEs, foundation models can gain substantial advantages in interpretability and accuracy compared to their counterparts in other fields. Incorporating physical priors gives PDE foundation models substantial advantages. Pure data-driven approaches offer expressiveness and efficiency but lack physical reasoning and interpretability. Physics-informed neural networks provide interpretability and lower sample complexity, but rely on rigid assumptions with poor generalization. Our question is that, how to combine both advantages by enforcing physics constraints within data-driven frameworks? Our physics-informed temporal alignment principle tackles this at two levels: physics level through soft constraint loss terms, and numerical level via consistency loss for temporal coherence. PITA has three components. First, we conduct auto-regressive prediction using normalized RMSE for data loss. Second, we conduct the data-driven governing equation discovery. We construct candidate term libraries and use Bayes regression with L0 regularization. Second, we conduct the data-driven governing equation discovery. We construct candidate term libraries and use Bayes regression with L0 regularization to identify dominant PDE terms. These coefficients become physics-informed constraints through PDE ratio loss. Third, we employ temporal consistence alignment by computing PDE coefficients from both ground truth and predictions. Then, we minimize their distance to ensure learned dynamics remain faithful to true governing equations. We adopt uncertainty-based multitask learning for automatic loss balancing and alternating direction optimization, updating PDE coefficients and model parameters iteratively. For in-distribution tests, PITA demonstrates superior performance over traditional autoregressive methods across multiple benchmarks. For out-of-distribution generalization, PITA outperforms standard methods on 75% of tasks when trained from scratch. Notably, fine-tuning pre-trained models yields inferior results, highlighting PITA's potential as a foundational training approach. Comparative analysis across 4 datasets shows PITA green line exhibits significantly less error accumulation over time compared to standard auto-regressive approaches, pink line. In conclusion, our method represents a significant step forward in developing robust, physically consistent PDE foundation models.